CLF calls. They are system calls used by applications. The third one is page fault handler. It manages additionally shared pages and the shared page table. The system memory is divided into two regions, private and shared. The private region is dedicated to each core, and a slash is allocated in this region. And the shared region is used for shared pages and shared page table. The shared page table has information about the shared pages. On top of our software's VM, you can run multi-threaded applications. We evaluated our software's VM, and here is our evaluation environment. We run 5 applications from Splash 2 benchmark. They are FFT, LUC, LUN, Redix, and OceanC. We inserted commit and reconcile operations manually and optimized them using our proposed technique. SSL 4A cores, and each core runs at 533 MHz. It has 32 GB of main memory. To show the effectiveness of our approach, we compare the scalability of applications with our application to the cache current machine. The machine we choose is AMD Optane system. It is a CC NUMA architecture, and it also has 48 cores. Each core runs at 2.2 GHz and 965 of main memory. Because two systems are very different, so we cannot compare the performance directly. So we just focus on the scalability of applications. Here's our evaluation result. The x-axis represents the applications, and y-axis represents speed up. The speed up is obtained over a single core. FFT, Redix, and OceanC, they don't have a result of 48 cores because they require the number of cores to be power of 2. In most cases, our software's VM is comparable to the CC NUMA architecture except Redix. In case of Redix, there are many spin-rate loops. Spin-rate loop requires a repeated reconcile operation in our software's VM. So it degrades the performance. To overcome this issue, we can modify our application by modify our application with a post-phase synchronization or supported by hardware. Here's our conclusion. We propose an efficient software shared virtual memory for the single-chip cloud computer. It is based on the CLF memory model. It does not need to modify legacy code, and it also does not need to complicate multiple layer protocols. Based on our result, our software's VM is compatible with the CC NUMA machine, so we foresee it can be an alternative to a hardware cache currency protocol. As a future work, we plan to develop a compiler with automatic code translation, and we plan to running more multi-threaded applications so we can prove our software's VM. Thanks for listening to my presentation. Questions?
Very interesting work. So you provide SVM to satisfy the programming. So my question is, could you allow to put the lock variable into the shared address space? The lock variable.
Yeah, actually, there's a shared test and set register in the SCC. So each core has one test and set register, so we can implement that lock. So actually, your customer's shared variable can be located in the shared page shared data, right?
Means that you can put the shared, the global variable into the shared address space, but my question is could you put the lock variable into the address space, shared address space?
Yeah, actually it's not possible in our case because the shared variable is actually the shared variable is copied to the local stage and then work the local stage. We perform load and general load and store operations performed in the local stage. So if the global variable is located shared region, then we copy the data to local stage and work in that space. So in that case, we cannot implement like that way. So if we want shared variable in the shared region, we have to give another kind of API, so we can use it.
Yes, sir.
Can you put the page before this? In this page. The results with the CCD1 machine seem to be strange. For example, the FFP benchmark achieves only, I think it's 3. Speed up with use 48 cores.
Yes.
This is kind of strange. Do you have an explanation for the result? Have you analysis why the CCD1 machine performs so poorly with these benchmarks?
Actually, I think I measured the total region of the execution of the application. There is a sequential region and parallel region. I think there are not enough parallel region in the application because the input size is not that large. In this case, in our software, the SCC core is not that powerful. But we compare two machines with same input data. So I think it's a kind of region.
As a author of the paper, I will answer that question. FFT is irregular application, okay, and it does not contain that much parallelism. That's the reason why we didn't get the poor, performance on CC/NUMA machine. Okay, so. Thank you.
So in the example loop you just presented, so I'm wondering if for the data you evaluate the results you presented, did you apply any implementations like partitioning or some loop parallel tactics? And if not, what do you see? How these optimizations affect the comparisons between CCNUMA and SCC?
You mean loop partitioning so that you can improve CCNUMA architecture, right?
Did you do any optimizations? Any traditional optimizations on the loops in the applications you tested?
Actually, we didn't, and we just compiled the original Splash benchmark source code, so we run it in the CCNUMA. And in our case, we just insert common reconciliation operation in that run. Right.
In the interest of time, we have to stop there. You can take the questions offline. Thanks.